In their pursuit to comprehend the first stars and galaxies that illuminated the cosmos, astronomers find themselves still grappling with uncertainty. However, with each discovery, they edge closer to enlightenment. This remarkable, undeniable truth emerges from the unprecedented findings of the James Webb Space Telescope, a $10 billion time machine now marking its inaugural year of observations. JWST is designed to unveil the faint infrared glow of the universe's earliest luminous objects and has exceeded expectations. Webb's vision extends back to the initial few hundred million years following the Big Bang, offering superior data on newborn galaxies compared to any previous facility. The abundance of galactic baby pictures has surpassed even the most optimistic projections, with dozens of candidate galaxies emerging much to the surprise of researchers like Charlotte Mason, an astrophysicist at the University of Copenhagen. The unexpected maturity of these early galaxies has prompted intense scrutiny and speculation among theorists and observers alike. Could these anomalous, large, and bright early galaxies be mere illusions, perhaps stemming from flaws in the telescope's initial observations? Or, if genuine, could they be reconciled within standard cosmological models? Alternatively, do they hint at a universe far stranger and more complex than previously imagined, possibly challenging the foundations of the Big Bang theory itself? Join us today as we delve into how the James Webb Space Telescope has reshaped our understanding of the cosmos. But first, let's rewind to the birth of the universe. Following the Big Bang, as the universe cooled, electrons, protons, and neutrons combined into mostly neutral hydrogen atoms, marking a period known as the Cosmic Dark Ages. Then a pivotal event occurred. Most of the universe's mass, composed of elusive dark matter, began exerting its influence, eventually leading to the formation of the first stars. These stellar beacons illuminated the cosmos during the epoch of reionization, sparking a cascade of events that shaped the evolution of galaxies within a vast cosmic web. Meanwhile, Edwin Hubble's groundbreaking discoveries in the 1920s revealed that the universe is expanding. Subsequent observations, including those from the Hubble Space Telescope, unveiled an even more astonishing truth. The universe's expansion is accelerating, driven by enigmatic dark energy, symbolized by the Greek letter lambda. By integrating the properties of cold dark matter, regular matter, and radiation into Einstein's general theory of relativity, scientists have constructed the lambda cold dark matter model, which remarkably aligns with a myriad of observational data. One way to validate this framework is by scrutinizing very distant galaxies, akin to peering back in time to the initial few hundred million years after the colossal explosion that set everything in motion. During this period, the cosmos was comparatively simpler, making it easier for astronomers to compare against theoretical predictions. The quest to glimpse the universe's earlier structures began with the Hubble telescope in 1995. Over 10 days, Hubble captured 342 exposures of what seemed like an empty patch of space in the Big Dipper. To astronomers' astonishment, this seemingly dark expanse revealed thousands of galaxies at various distances and stages of development, stretching back much further in time than anticipated. In 2016, astronomers made a groundbreaking discovery with Hubble, the most distant galaxy known at the time, dubbed GNZ11. This faint smudge dated to approximately 400 million years after the Big Bang and challenged conventional notions of early galaxy formation. However, it did not fundamentally undermine the lambda cold dark matter model, partly due to its diminutive size, comprising only 1% of the Milky Way's mass. Yet astronomers needed a more potent tool to discern whether GNZ11 was an anomaly or part of a broader cohort of enigmatic early galaxies. Enter the James Webb Space Telescope, renowned as the largest and most potent observatory ever launched from Earth. Positioned 1.5 million kilometers away from earthly interference and cooled to near absolute zero, JWST carries a massive segmented mirror and highly sensitive instruments designed to unveil never-before-seen details of cosmic dawn. JWST's initial discoveries have already surpassed expectations, offering glimpses of galaxies astonishingly close to the dawn of time and probing exoplanet atmospheres with unprecedented precision. As Webb's vision extends back to the universe's earliest epochs, it promises to yield unparalleled insights into newborn galaxies, potentially reshaping our understanding of cosmic evolution. The implications of JWST's early revelations are profound, potentially rewriting the opening chapters of cosmic history and shedding light on fundamental questions about our existence in the universe. As Mark McCaffrey, a senior advisor for space and exploration at the European Space Agency, aptly noted, these machines are designed not to affirm the status quo, but to challenge it, paving the way for paradigm-shifting discoveries. A key method utilized by researchers to assess the distances of celestial objects is a variant of the Doppler effect, analogous to determining the location of an ambulance based on the pitch of its siren. Astronomers measure the redshift of galaxies, where the magnitude of redshift indicates the object's distance from us. JWST's data has already led to intriguing findings, such as the discovery of galaxies with redshift values ranging from 11 to 20, hinting at the possibility of an incomplete understanding of early galaxy formation within the lambda cold dark matter model. In summary, JWST's unprecedented capabilities have begun to unravel the mysteries of the early universe, challenging existing models and paving the way for a deeper understanding of cosmic evolution. Researchers delved into computer simulations of universes governed by the lambda cold dark matter model and made a startling revelation. The early bright galaxies observed by JWST were significantly more massive than those simulated to form concurrently. This dissonance sparked debates within the scientific community and garnered attention from various media outlets, with some claiming that JWST was challenging the foundations of cosmology. However, not all experts were swayed by these assertions. One inherent challenge lies in the ambiguity of lambda cold dark matter's predictions. While concepts like dark matter and dark energy are relatively straightforward, visible matter exhibits complex interactions and behaviors, especially in the tumultuous early years following the Big Bang. These chaotic times must be approximated in computer simulations, introducing uncertainties into the models. Another complication arises from the difficulty in accurately determining the distances of galaxies. In the months following the initial papers, the ages of some purported high redshift galaxies were reassessed due to updated telescope calibrations. For instance, Suarez 749 was found within a galaxy cluster whose light dates back 12.4 billion years, suggesting it might be a nearer object masquerading as a high redshift galaxy due to dust obscuration. NAU, among others, highlighted the potential existence of new types of galaxies, confounding researchers. While JWST images captivated astronomers and the public alike, researchers worked diligently behind the scenes to discern the true nature of the observed galaxies and refine the parameters of cosmological equations. Key among these parameters is the mass of early galaxies, crucial for assessing their growth over time and reconciling with lambda cold dark matter predictions. Determining a galaxy's mass from its brightness relies on assumptions grounded in our understanding of stars and galaxies. However, Megan Donahue, an astrophysicist at Michigan State University, cautions that this relationship is at best an educated guess. It hinges on assumptions regarding the initial mass function, which dictates the statistical range of masses in which stars typically form. The initial mass function assumption is crucial because while hot, blue, massive stars emit more light, the majority of a galaxy's mass resides in smaller, cooler, red stars. Yet it's plausible that the initial mass function varied in the early universe. If so, the early galaxies observed by JWST might appear brighter than they actually are, potentially challenging our understanding of galaxy formation. Rachel Somerville, an astrophysicist at the Flatiron Institute, suggests that tweaks to the initial mass function or other factors could reconcile the ancient galaxies observed by JWST with the lambda cold dark matter model. She posits that perhaps gas in the early universe cooled and condensed more rapidly, leading to faster star formation. Another intriguing possibility is the role of black holes in the early cosmos. Glowing supermassive black holes observed at redshifts of 6 or 7 billion years after the Big Bang could explain the brightness of early galaxies, even if they aren't exceptionally massive. Confirmation that the lambda cold dark matter model can accommodate some of JWST's early galaxies came from simulations conducted by Benjamin Keller and his team at the University of Memphis. Their findings, reported on the preprint server arcs4.org, indicate that the simulated galaxies align with JWST observations, alleviating concerns about the compatibility of the observed galaxies with the prevailing cosmological model. Furthermore, JWST's discoveries hint at the existence of population 3 stars, the first generation of stars to ignite. These stars, unpolluted by metals from previous stellar generations, may have contributed to the reionization of the universe. The revelation of shockingly massive and old galaxies in the early universe, as observed by the James Webb Space Telescope, initially rattled astronomers' fundamental understanding of the cosmos. Dubbed universe breakers, these galaxies defied expectations and raised questions about the validity of the standard model of cosmology. However, recent insights suggest that the model can accommodate JWST's discoveries. Computer simulations guided by the standard model have demonstrated that the universe could plausibly produce galaxies like those observed by JWST. While the data initially appeared inconsistent with cosmological models, astronomers now speculate that gaps in our understanding of galaxy formation may be the root cause. Possible explanations for the unexpected findings abound. Some propose that early stars formed more efficiently than previously thought, while others suggest that cosmic dust in these galaxies could distort their appearance, making stars seem older. Additionally, the role of black holes, particularly in amplifying galactic brightness, is under scrutiny. Yet despite these potential explanations, the sheer size and age of the observed galaxies remain puzzling. Further observations, particularly those involving spectroscopy to analyze starlight in greater detail, are essential for confirming the nature of these galaxies. As astronomers delve deeper into these mysteries, anticipation builds for the forthcoming spectroscopic data expected this spring. This endeavor represents a journey of exploration and discovery, pushing the boundaries of our understanding of the universe's infancy. The success of JWST's first year of observations has set the stage for even more intriguing discoveries in its second year, or Cycle 2. However, the competition for observing time on JWST is fierce, with only a fraction of proposed projects selected for Cycle 2. Despite the disappointment for some, the rigorous and anonymous selection process ensures fairness and integrity in determining JWST's scientific priorities. Despite the fervent competition for observing time on the James Webb Space Telescope, not all astronomers found success in securing time for their proposed projects. Nathan Adams of the University of Manchester, for instance, expressed disappointment as none of his 4 proposals were accepted. Conversely, Marion Labeck of Texas A&M University celebrated the approval of 3 proposals, all focused on studying white dwarfs, the remnants of sun-like stars. Labeck's research aims to confirm the existence of suspected white dwarf worlds potentially harboring intact planets. By studying these stellar remnants, researchers hope to gain insight into the fate awaiting Earth when our sun evolves into a red giant in billions of years. In Cycle 2, the focus on the TRAPPIST-1 system, a set of 7 Earth-sized planets orbiting a red dwarf star, continues. While 3 programs were selected in Cycle 1, only one has been chosen this time, led by Michael Gillen of the University of Liège in Belgium. Michael Gillen aims to study the atmospheres of TRAPPIST-1b and TRAPPIST-1c, the 2 innermost planets of the TRAPPIST-1 system. Previous studies suggested that TRAPPIST-1b might lack an atmosphere, but Gillen plans to use a technique measuring temperature differences between the day and night sides of the planet to confirm this and explore implications for the system's potentially habitable worlds. Christopher Glenn from the Southwest Research Institute in Texas plans to use JWST to study Saturn's moon Enceladus, which may have a habitable ocean beneath its icy surface. Glenn hopes to detect evidence of ocean chemistry on Enceladus's surface, including substances like ammonia and organic molecules, which could provide insights into the moon's habitability. However, not all proposed projects received approval. David Kipling of Columbia University had his proposals to search for exomoons orbiting exoplanets rejected. Despite the disappointment, Kipling emphasizes the significance of this research, as the detection of exomoons could challenge current models of our solar system and provide valuable insights into cosmic norms. Nancy Levinson of the Space Telescope Science Institute acknowledges the inevitable disappointments from unselected programs, but encourages researchers to continue striving for opportunities in future cycles. With the deadline for Cycle 3 proposals approaching, there's still hope for scientists to pursue their research goals using JWST. Overall, The selected programs represent a diverse range of scientific inquiries, showcasing JWST's potential for groundbreaking discoveries across various fields of astronomy. As Levinson highlights, there's much more to uncover, and JWST's journey of exploration is far from over.